In this video, we're going to talk about single displacement reactions and how we would predict the products for such a reaction. Our goal is to predict what the products would be based on the given reactants. Originally, the directions of this worksheet state that we're going to use the activity series to figure this out, but we're just going to assume that all of these reactions go to completion. So let's take a look at the first one. In this first example, we have magnesium, which is a metal, and that metal will form a cation when bonded in an ionic compound. So that metal is going to switch with the metal that exists already in the ionic compound that is a reactant. So if you take a look at our example template, A and B, both representing cations, are going to switch places. So we know that in the products, B, which in this case would be zinc, is going to become its own element by itself. Then A will be bonded to C. So what's left is magnesium bonded to chlorine. However, it's not that simple. Because we're writing the formula of an ionic compound, we need to recall that the charges, magnesium being a positive 2 and chlorine being a negative 1, must balance out to 0. So we need 2 chlorines. Magnesium chloride is going to be one of our products in this single displacement reaction. Let's take a look at the second example. Zinc and copper are both cations when part of ionic compounds. So again, in this single displacement reaction, our zinc and our copper are going to switch places. So copper is going to become its own element by itself, and zinc is now going to be bonded with nitrate, NO3. But again, we have to make sure we balance the charges because we're writing the formula of an ionic compound. Zinc always gets a positive 2 charge, nitrate gets a negative 1. So we must make sure that we put parentheses and a subscript of 2 around our nitrate ion so that we can show that the formula has a charge of 0. This equation and number 1 are both already balanced as is. If we take a look at number 3, this one's a little bit trickier because we don't know the charge of nickel in this compound when it makes the single replacement reaction. So I would have to tell you that. Let's assume that nickel is going to get a positive 2 charge here. You wouldn't be able to know that unless I told you. So again, in this case, we're going to see nickel, because it's a cation, switching places with aluminum, also a cation. So aluminum is going to be by itself, and now we need to write the chemical formula for the resulting ionic compound between nickel and sulfate. Nickel, we just said, is going to get a positive 2 charge because that's what I mentioned, and sulfate is SO4. It's also going to get a negative 2 charge. That's according to your periodic table, the back of your periodic table where your polyatomic ions list is. So this formula is already balanced. Now that we've balanced the chemical formula so that it has an overall charge of 0, then we can balance the actual chemical equation. I can see that there's 1 nickel on each side, so that's okay. I notice there's 2 aluminum and 1 aluminum, so I'm going to have to do something there. And there's 3 SO4 and 1 SO4. So I'm going to start by putting a 3 in front of my nickel sulfate. So I have the same number of sulfate on both sides. I'm going to include a 2 in front of my aluminum and a 3 in front of my individual nickel. So my equation is balanced. Right now you might notice that we are going to ignore states of matter. Right at this point I am just focused on making sure we can understand how to actually predict what the products are based on our template reaction of the single replacement reaction. So I'm going to jump down to number 5. Oftentimes you're going to see tricky ones like this where you've got hydrogen and oxygen together in water looking at a single displacement reaction. When this happens, you can actually rewrite the water as HOH, hydrogen with a positive 1 and hydroxide with a negative 1. It's essentially the same thing. So again, you can see that silver, being a cation, is going to switch places with the cation in the compound. So same thing happens here. We get hydrogen by itself, but remember it's a Honkelbrief element, plus silver bonded to hydroxide. There's your single replacement reaction with silver and water. Then, finally, we've seen a bunch where we had the single element was a metal. However, this time in number 6, our single element is an anion or a nonmetal. So it's not going to switch with Na, it's actually going to switch with Br. So alone now is going to be Br, which is a Honkelbrief, so it needs a 2, plus sodium, which will be bonded to chlorine in an ionic compound, sodium having a positive 1, chlorine having a negative 1. One of each will be sufficient to have an overall neutral compound. And there is our example where the lone element is actually an ion. Stay tuned for the second half of this video where we will talk about double replacement reactions. The next type of reaction that we're going to predict products for is a double displacement reaction. And at this point, I'm going to also show you how to use the solubility table of common ions found on your green reference sheet below your list of polyatomic ions. So take a second, make sure you have that out. So at this point, our goal is to use the double displacement or double replacement reaction template to determine what our new products are going to be. In this case, our cations are going to switch places. So in the first example, Pb and K are going to flip-flop. Pb is going to be bonded to SO4 and K will be bonded to NO3. The important thing to remember here is that we must make sure that we are writing chemical formulas that have balanced charges. We can't just pair up K and Pb in the same ratio that they were paired up with before. So Pb will now be bonded with SO4. Here, NO3 has a negative 1 charge, and there are 2 of them. So that must mean that Pb has a positive 2 charge to balance that out. So Pb with a positive 2, and sulfate always has a negative 2. So this means that we can rewrite the formula as PbSO4 without any additional subscripts because the formula is already balanced. Then we are going to write the chemical formula for when K, potassium, is bonded to nitrate. Potassium has a positive 1 charge, nitrate has a negative 1, so only one of each is necessary. Commonly, people will take the subscript here and just stick it over here as well, but that is not the correct way to approach this problem. Additionally, what we're going to have to do is identify if this product or these products are either aqueous or precipitates, meaning solid. So PbNO3, we're going to assume that's an aqueous reactant, and we're going to assume K2SO4 is an aqueous reactant. I'm telling you this is true, and on a test I would also let you know whether or not these reactants were aqueous or solid or liquid or gas. So now what we need to do is use that solubility table to show whether or not lead sulfate is going to be soluble or insoluble, and if KNO3 will be soluble or insoluble. If neither of the products are insoluble, meaning neither of them are going to become solid when the chemical reaction occurs, then you will have no reaction. I'll show an example of that a little bit later, but in this case, we are going to see a reaction occurring. So what we're going to do is look at our cation and our anions. We've got Pb and we have SO4. So we're going to go ahead and look at the groups, and we're going to look for lead group or sulfate group. Here's a sulfate group, and it says most sulfates are soluble in water, unless the sulfate is bonded to one of these elements. Our sulfate is bonded to Pb. So that means that PbSO4 is insoluble. So what that means is we are going to have a solid being created in this chemical reaction. Then we have to look at the second product. We're going to look for either K or NO3. Here's our first group of alkali metals. K is part of that. All alkali metals, when bonded in an ionic compound, are soluble. None of them are insoluble. Soluble means it dissolves in water, which means we are going to have an aqueous solution as our product for KNO3. Because this solid formed, we have a chemical reaction. So let's take a look at another example. H2SO4 reacting with KOH. So again, we're going to take a look at our reactants and we're going to swap the cations. So now hydrogen is bonded to the hydroxide group. HOH, that looks pretty familiar. It's actually the same thing as writing H2O. We know H2O is a liquid. We're going to again assume that our reactants are aqueous. Now we have to write our chemical formula for K bonding with SO4. Potassium always has a positive 1, sulfate has a negative 2. K2SO4 is going to be our chemical or our product here. So water we already know is a liquid. K2SO4, remember all potassium ions are soluble, meaning this is an aqueous solution. Because we have the formation of this liquid, this reaction will also occur. We're going to skip down to number 4, where we have copper chloride, and this has to be copper 2 chloride because chlorine has a negative 1, there's 2 of them, and there's 1 copper. So copper must have a positive 2 charge. So again, we're going to swap the cations. Sodium and copper are going to switch partners. So copper is now going to be bonded, and remember it has a positive 2 charge, to PO4 phosphate, which has a negative 3 charge. So we have to make sure that we write the balanced chemical formula for copper 2 phosphate. I know that I need 2 negative 3s to balance out 3 positive 2s. So that's my chemical formula for copper 2 phosphate. And again, I'm going to take a look at my solubility chart. Phosphates, PO4, they're soluble when bonded to alkali ions, meaning your K, Li, Na, but most times when you have a phosphate, it's going to be insoluble. So that means, since copper is not an alkali metal, this compound is a solid. Then we also have a second compound formed. Na is going to be bonded to Cl, and in this case, sodium has a positive 1, chlorine has a negative 1, one of each is required. All sodium ions are soluble. This is an aqueous solution. And we'll do one more. We'll do number 6. Calcium is going to switch places with silver. So calcium and nitrate. Calcium has a positive 2, nitrate a negative 1. So CaNO3, but there must be 2 NO3 groups to balance out the positive 2 from the Ca. All nitrate groupings are soluble. So that means this is going to be an aqueous solution. And silver, Ag, which always gets a positive 1 charge, is going to be bonded with chlorine, which gets a negative 1. AgCl is got a balanced formula. Let's find either silver or chlorine in our groups. Here's chlorides. Most chlorides are soluble unless they are bonded to silver, mercury, or lead. Our silver is bonded to chlorine, so this is going to be insoluble, meaning we have a solid. Hopefully these examples were helpful for you. We'll go over them in class the next time we meet, and your homework is packet pages 36 and 37, starting with the odds.